traveling at light speed should let you cross the galaxy in seconds, right? Wrong. At light speed, you wouldn't experience time at all. The journey would be instantaneous, but also impossible. This is the paradox that breaks our understanding of reality. If you're fascinated by the mysteries of space, hit that subscribe button. You'll join a community of curious minds. Let's get started. Let's imagine that we could somehow cheat physics. Let's say some advanced technology we haven't discovered yet allows you to reach light speed. What would you experience? You've probably heard that time slows down as you approach light speed. This is called time dilation, and it's not science fiction, it's verified science. Here's how it works. Imagine you have a twin sibling. You board a spacecraft and accelerate to 90% light speed, then travel for what feels like 1 year to you before returning home. When you step off that spacecraft, you discover that your twin has aged more than 2 years. The faster you travel, the more dramatic this effect becomes. At 99% light speed, 1 year for you equals about 7 years for everyone else. At 99.9%, 1 year for you equals 22 years back home. At 99.99%, 1 year for you equals about 70 years on Earth. Now here's the truly strange part. If you could reach exactly light speed, time dilation becomes infinite. From your perspective, time would stop completely. The journey from one end of the universe to the other would seem instantaneous. You'd depart and arrive in the same moment. No time would pass for you at all. But here's the paradox. From the perspective of everyone else in the universe, you'd still be traveling for billions of years because they'd see you moving at light speed, covering vast distances over vast time spans. You'd experience zero time, but the universe would age around you. This is what physicists mean when they say that photons, particles of light, don't experience time. A photon created at the Big Bang 13.8 billion years ago experienced no time at all, even though it's been traveling through space for the entire history of the universe. This gets even stranger when we consider what you'd actually see during your journey. If you're fascinated by the extreme challenges of traveling between stars, you'll definitely want to check out my video on the real reason we can't survive interstellar travel, where we dive deep into the practical obstacles that make journeys through space so incredibly dangerous. Now, let's talk about what the universe would look like from your perspective as you accelerate toward light speed. This is where reality becomes more spectacular than any movie special effects team has ever imagined. As you accelerate, you'd notice something called the Doppler effect. You're probably familiar with this from everyday life. When an ambulance races toward you, its siren sounds higher pitched, and as it speeds away, the pitch drops. The same thing happens with light. Light coming from stars ahead of you would be blue shifted, meaning the wavelengths compress and shift toward the blue end of the spectrum. Light from stars behind you would be red shifted, stretching toward the red end and beyond into infrared, eventually becoming invisible to your eyes. But that's just the beginning. As you approach light speed, something called relativistic beaming occurs. The stars wouldn't just change color, they'd appear to move. Stars that were originally scattered across the entire sky would seem to gather in front of you, concentrating into a smaller and smaller circle directly ahead. At 99% light speed, almost all the visible stars would appear compressed into a cone about 30 degrees wide in front of your spacecraft. At 99.9%, that cone shrinks to about 9 degrees. The entire magnificent panorama of the cosmos would appear squeezed into a tunnel of light ahead of you, while the space behind and around you would appear almost completely black. And here's something even more spectacular: the cosmic microwave background radiation, the leftover glow from the Big Bang that permeates all of space, would become visible to your naked eye. Normally, This radiation has wavelengths in the microwave range, invisible to human eyes. But as you race through space at near light speed, this radiation would be blue shifted into visible light. The universe itself would seem to glow with an eerie radiance. Scientists at institutions like NASA's Goddard Space Flight Center and the European Space Agency have created computer simulations of what you'd see, and the results are breathtaking. You wouldn't see the star streak effect from movies like Star Wars. Instead, you'd see a brilliant, concentrated burst of light ahead of you, with colors shifting from red through the spectrum to blue and beyond into ultraviolet, while space around and behind you dims into darkness. Now, let's discuss something that science fiction often gets wrong, but science gets frighteningly right. What would happen to your body during this journey? Even before we address the impossibility of reaching light speed itself, we need to talk about acceleration, because getting to near light speed would be absolutely devastating to any human body if done too quickly. Your body can handle about 5 times Earth's gravity, or 5 Gs, for a short period. Fighter pilots experience around 9 Gs during extreme maneuvers, and they require special suits and training to avoid blacking out. But to reach even a fraction of light speed in a reasonable time frame, you'd need acceleration far beyond what any human could survive. Let's do some calculations. If you accelerated at a constant 1 G, which would feel exactly like standing on Earth's surface, it would take you almost a year, specifically about 354 days, to reach light speed if physics allowed it. That's the gentlest possible journey, and it would still require an amount of energy that staggers the imagination. But here's a reality check from NASA's current technology. The Parker Solar Probe, launched in 2018, is the fastest human-made object ever created. At its maximum velocity, it reaches about 192 kilometers per second. That sounds impressive until you realize it's only 0.064% the speed of light. We'd need to go over 1,500 times faster to reach light speed. The propulsion requirements are almost incomprehensible. According to calculations by physicists at institutions like MIT and Caltech, accelerating even a small 1,000-kilogram spacecraft to just 50% light speed would require more energy than humanity currently produces in an entire year. And remember, due to that mass increase we discussed, the energy requirements grow exponentially as you approach light speed. But let's imagine you've somehow solved the energy problem and you're accelerating smoothly at 1 G toward light speed. Your body feels normal, like you're just standing on Earth. But something else would kill you long before you reached your destination. Radiation. Space isn't empty. Even in the vast darkness between stars, there are particles. Hydrogen atoms, mostly, about 1 per cubic centimeter in interstellar space. At everyday speeds, these particles are harmless, but at relativistic speeds, speeds approaching light speed, these atoms become deadly projectiles. Here's why. When you're moving at 99% light speed and you collide with a hydrogen atom, from your reference frame, that atom is hitting you at 99% light speed. The kinetic energy is enormous. Each collision would release high-energy radiation, similar to gamma rays. Your spacecraft would be bombarded with what's essentially a continuous beam of deadly radiation. Dr. William Edelstein, a physicist at Johns Hopkins University, calculated that at just 95% light speed, the radiation dose from interstellar hydrogen would be about 10,000 Sieverts per second. To put that in perspective, 5 Sieverts is usually fatal to humans. You'd receive a lethal dose in less than a millisecond. Your cells would be destroyed at the molecular level before you could even perceive what was happening, and it gets worse at higher speeds. At 99.9% light speed, the radiation intensity increases proportionally. You'd need shielding so thick and so heavy that it would make the journey even more impossible from an energy standpoint. This is one of the harsh realities that science fiction often glosses over. The movies show sleek spaceships zipping between stars, but they rarely address the fact that at those speeds, even a speck of dust becomes a catastrophic impact, and even the thin gas between stars becomes a lethal radiation hazard. Researchers at the Tau Zero Foundation and other organizations studying interstellar travel have proposed various shielding concepts: magnetic fields to deflect charged particles, thick layers of hydrogen-rich materials to absorb radiation, or even using a disposable shield of ice or metal at the front of the spacecraft. But all of these solutions add mass, which means you need even more energy to accelerate. Which brings us back to the fundamental problem. Now, let's explore something that might surprise you. Not everything in the universe is limited by light speed in the way you might think. While nothing can move through space faster than light, space itself can expand faster than light. And this tells us something profound about the nature of reality. When astronomers look at distant galaxies, they've discovered something astonishing. The universe isn't just expanding, it's accelerating. Galaxies far enough away from us are receding faster than light because the space between us and them is expanding so rapidly. This discovery, made in 1998 by two teams of astronomers studying distant supernovae, earned Saul Perlmutter, Brian Schmidt, and Adam Riggs the Nobel Prize in Physics in 2011. Think about this. There are galaxies so distant that their light will never reach us, no matter how long we wait, because the space between us is expanding faster than their light can travel through it. We're surrounded by a cosmic horizon, beyond which we can never see, never visit, never communicate with. It's one of the most humbling discoveries in all of science. This expansion is driven by something we call dark energy, a mysterious force that makes up about 68% of the universe. We don't know what it is, we don't understand how it works, but we can measure its effects, and those effects tell us that the fabric of space itself doesn't obey the same speed limit that applies to objects moving through space. This distinction is crucial. Light speed is the ultimate speed limit for information, for cause and effect, for anything moving through space, but space itself plays by different rules. Einstein's equations allow for this, and observations confirm it. Some physicists have speculated about technologies that could exploit this loophole. The concept is called a warp drive, popularized by science fiction, but actually grounded in real physics equations. In 1994, physicist Miguel Alcubierre published a paper showing that Einstein's equations technically allow for a warp bubble that contracts space in front of a spacecraft and expands it behind, allowing the ship to effectively travel faster than light without actually moving through space at light speed. Before you get too excited, there are enormous problems with this idea. The original Alcubierre drive calculations required more energy than exists in the entire observable universe, and specifically required a form of matter with negative mass, something we've never observed and that may not exist at all. However, research continues. In 2021, physicist Eric Lentz proposed a modified approach that in theory wouldn't require negative energy. In 2024, researchers at institutions including DARPA's Limitless Space Institute continued exploring whether any version of this concept might be physically possible. The consensus among physicists is that it remains highly speculative, but it hasn't been completely ruled out by known physics. What does this tell us? It tells us that the universe is far stranger and more subtle than our everyday intuition suggests. The speed of light isn't just a speed limit, it's woven into the fundamental structure of space-time itself. It's the speed at which causality propagates, the speed at which information travels, the cosmic constant that connects space and time. Let's talk about why this speed limit exists at all. Why 299,792 kilometers per second? Why not faster? Why not slower? The answer reveals something beautiful about the universe's design. The speed of light falls out naturally from the equations of electromagnetism first unified by James Clerk Maxwell in 1865. When Maxwell combined all the known laws of electricity and magnetism into a single set of equations, he discovered that these equations predicted waves that would travel at a specific speed, a speed determined by two fundamental constants: the permittivity and permeability of free space, essentially how electric and magnetic fields behave in vacuum. When Maxwell calculated this speed, he got approximately 300,000 kilometers per second. He realized he'd discovered what light actually is, an electromagnetic wave. And the speed wasn't arbitrary. It emerged from the basic properties of electric and magnetic fields. Einstein took this insight even further. He realized that Maxwell's equations gave the same value for the speed of light regardless of how you were moving when you measured it. This seems impossible at first. If you're on a train moving at 100 kilometers per hour and you throw a ball forward at 20 kilometers per hour, someone standing still on the platform would measure the ball moving at 120 kilometers per hour. Speeds add together, right? But light doesn't work that way. If you're in a spacecraft moving at half the speed of light and you shine a flashlight forward, you don't measure the light leaving your flashlight at 1.5 times light speed. You measure it at exactly light speed, and incredibly, someone watching from a stationary position would also measure that same light beam traveling at exactly light speed, not at 1.5 times light speed. This bizarre fact, confirmed by countless experiments over more than a century, forced Einstein to rethink the nature of space and time themselves. He concluded that space and time must be flexible, must warp and stretch, in order to keep the speed of light constant for all observers. This was the birth of special relativity. The speed of light isn't just the speed of light. It's better understood as the speed of causality, the maximum speed at which cause and effect can propagate through the universe. It's the conversion factor between space and time, the thing that binds them together into space-time. In the equations of relativity, the speed of light plays the same role that infinity plays in mathematics. It's a boundary, a limit that shapes everything else. Some physicists prefer to call it the speed of massless particles, because anything without mass, photons of light, gravitons that carry gravity, and certain other particles must travel at this speed. They have no choice. Massless particles can't travel slower than light speed, and massive particles can't reach it. The universe has this built-in divide between two kinds of existence. Now let's explore what this cosmic speed limit means for our dreams of exploring the galaxy. The Milky Way galaxy is about 100,000 light-years across. That means light takes 100,000 years to cross from one side to the other. Our nearest neighboring star, Proxima Centauri, is 4.24 light-years away. If you could somehow travel at 99% light speed, you could reach Proxima Centauri in about 4.3 years from Earth's perspective. But here's where time dilation becomes your friend. From your perspective on the spacecraft, due to time dilation, the journey would feel like only about 7 months. You'd age 7 months while Earth aged 4.3 years. Push it to 99.99% light speed, and from your perspective, you could cross the entire galaxy, 100,000 light-years, in just about 140 years of experienced time. You could visit the center of our galaxy and return within a human lifetime from your own perspective. But when you got back to Earth, over 200,000 years would have passed. Everyone you knew would be dead. Human civilization might not even exist anymore. You'd be a time traveler to the distant future with no way back. This creates what's called the twin paradox. though it's not really a paradox once you understand relativity. Imagine you have a twin and you take off on a journey to a star 10 light-years away at 99.5% light speed. You travel there and back, so 20 light-years total distance. From Earth's perspective, your journey takes about 20 years and 1 month. But on board your spacecraft, thanks to time dilation, only about 2 years pass. When you return, you're 2 years older, but your twin has aged 20 years. You're now 18 years younger than your twin, even though you were born at the same moment. This isn't science fiction. This is what Einstein's equations, confirmed by every test we've thrown at them, tell us must happen. The effect has been measured with atomic clocks on aircraft, with particles in accelerators, and with GPS satellites orbiting Earth. Those satellites experience time slightly differently than we do on the surface, and if we didn't account for relativistic time dilation in their programming, GPS navigation would be off by kilometers within days. This raises philosophical questions that have puzzled thinkers for over a century. If you could travel near light speed, you could journey to the far future, but you could never return to your own time. You'd be an exile from your own era, moving only forward through time at an accelerated rate. Some have called this the loneliest journey imaginable. Science fiction author Joe Haldeman explored this in his novel The Forever War, published in 1974, where soldiers fighting an interstellar war experience only months between battles, but return to an Earth where decades or centuries have passed. Each time they come home, it's to a world more alien than the last. But there's another aspect we haven't discussed yet. What would happen to you at light speed from the perspective of the fundamental forces of nature? This is where quantum mechanics and relativity intersect in fascinating ways. At the quantum level, the universe is governed by 4 fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. These forces hold atoms together, govern chemical reactions, keep you stuck to the planet, and power the stars. But these forces propagate at light speed. Electromagnetic force, the force that holds molecules together and gives matter its structure, travels at light speed. When atoms interact, they do so by exchanging photons, particles of light. These interactions happen at light speed. If you were somehow traveling at light speed, the electromagnetic forces within your body would behave strangely. From your perspective, time would have stopped, which means the electromagnetic interactions that maintain your body's structure would effectively freeze. You couldn't think, because thinking requires electrical signals traveling through neurons, and those signals propagate at much slower than light speed, but still require time to pass. You couldn't see because seeing requires photons to enter your eye and trigger chemical reactions, processes that require time. In a very real sense, if you could reach light speed, you would cease to exist as a functioning, thinking, living being. You'd be frozen in time, unchanging, unable to experience anything at all. Only when you slowed down would time resume for you. This is part of why photons don't experience time. A photon doesn't have a perspective in any meaningful sense. It's created. It travels what might be billions of light years from our perspective, and it's absorbed, all in the same instant from the photon's non-existent reference frame. The more you think about this, the stranger it becomes. Time and space aren't the fixed stage on which events happen, as Newton thought. They're dynamic, flexible, interwoven aspects of a single thing. Space-time. Your motion through space determines your motion through time. Move faster through space and you move slower through time, always in such a way that your total speed through space-time equals the speed of light. Let me explain that last part because it's one of the most beautiful insights in all of physics. Right now, sitting still or moving slowly, you're racing through time at essentially the full speed of light. Every second you move 1 second into the future, But as you accelerate through space, you start moving through space faster and through time slower. Some of your motion through time gets redirected into motion through space. A photon moves through space at light speed, which means it has zero motion left over for moving through time. It's using all of its motion through space-time to move through space, leaving nothing for movement through time. You're doing the opposite. Nearly all of your motion through space-time is through time, with very little through space. This framework, where everything moves through space-time at light speed, but divides that motion between space and time differently depending on velocity, is called the four-velocity in physics. It's a way of understanding why the speed of light is so special. It's not just a speed limit, it's the rate at which everything in the universe moves through space-time itself. Now let's discuss something that connects this cosmic speed limit to the very existence of matter itself, mass and energy equivalence. Einstein's famous equation, E=mc², tells us that mass and energy are interchangeable, two forms of the same thing. The c in that equation is the speed of light, and it's squared, making it an enormous conversion factor. Take 1 kilogram of matter, any matter at all. If you could convert all of that mass into pure energy, you'd release 9 times 10 to the power of 16 joules. That's 90 million billion joules, roughly the energy of the largest nuclear weapon ever tested, the Soviet Tsar bomber, detonated in 1961. 1 kilogram contains that much energy, locked up in the mass itself. This is why nuclear weapons and nuclear power work. They convert a tiny fraction of mass into energy, following Einstein's equation. In a nuclear reaction, less than 1% of the mass becomes energy, and it's enough to power cities or destroy them. If we could achieve 100% conversion, the energy from a coin would power a city for days. But here's what this has to do with light speed. The equation also works in reverse. Energy has mass. When you add energy to something, you increase its mass. And as you accelerate something to higher and higher speeds, you're adding kinetic energy to it, which increases its mass, which requires more energy to accelerate further in an endless cycle that makes reaching light speed impossible. This isn't just theoretical. At the Large Hadron Collider, protons are accelerated to 99.99991% light speed. At that velocity, each proton has about 7,000 times more mass than when it's sitting still. The protons haven't gotten bigger, they haven't gained any particles, but their energy has increased so dramatically that their effective mass has multiplied 7,000-fold. To push those protons just a tiny bit faster to 99.99999% light speed would require enormously more energy. To reach 100% would require infinite energy, which the universe simply doesn't have to offer. This creates an asymptote, a mathematical boundary that you can approach but never reach. You can get to 99% light speed, 99.9%, 99.99%, adding more and more nines, but you'll never reach 100%. The universe has drawn a line, and that line is absolute. Some people wonder if there might be particles that travel faster than light. Hypothetically, these particles, called tachyons, would always travel faster than light, just as normal particles always travel slower. But here's the problem. If tachyons exist, they would have imaginary mass, meaning their mass would be the square root of a negative number, something that doesn't make physical sense in our understanding of reality. Moreover, faster-than-light particles would violate causality. They could carry information backward in time, allowing effects to precede their causes. You could receive a message before it was sent. This creates paradoxes that seem to make the universe logically inconsistent. Most physicists believe tachyons don't exist, and we've never detected any evidence of them despite decades of searching. Every time we've seen reports of faster-than-light phenomena, They've turned out to be measurement errors or misunderstandings. In 2011, the Opera experiment in Italy reported detecting neutrinos that appeared to travel faster than light. The physics community was skeptical, and rightfully so. Further investigation revealed the measurement was wrong, caused by a faulty cable connection and a clock synchronization error. When corrected, the neutrinos traveled at exactly the speed physics predicted, just slightly slower than light. This is how science works. Extraordinary claims require extraordinary evidence, and when evidence contradicts well-established theories that have passed thousands of tests, the first assumption should be that the new measurement is wrong, not that our entire understanding of the universe needs to be rewritten. But let's imagine a different scenario. What if you couldn't reach light speed, but you could reach 99.9999% of it? What would that journey be like? What could you accomplish? At this speed, time dilation becomes extreme. 1 year for you would equal about 2,236 years for everyone else. You could travel to Andromeda, our nearest large galaxy neighbor, 2.5 million light-years away, and from your perspective, the journey would take only about 1,119 years. That's still longer than recorded human history, so you'd need some form of suspended animation or generation ship, where multiple generations are born and die during the voyage, but it's at least within the realm of imaginable human timescales. The catch? When you arrived at Andromeda, over 2.5 million years would have passed on Earth. Humanity might have evolved into something unrecognizable. Our species, Homo sapiens, has only existed for about 300,000 years. In 2.5 million years, we might have branched into multiple species, gone extinct, or transcended biological form entirely. You'd be traveling not just to another galaxy, but to a future so distant that everything you knew would be ancient history. This is the cruel bargain that relativity offers. You can travel vast distances within your lifetime, but only by exiling yourself from your own time forever. There's no going back, not in space and not in time. Some scientists have proposed using this effect intentionally. If humanity faced an extinction-level threat, a catastrophe we couldn't prevent, we could potentially send a small group on a near-light-speed journey. While only decades or centuries passed for them, millions of years could pass on Earth, giving the planet time to recover. The travelers could return to reseed human civilization on a healed world. This concept appears in science fiction, but it's grounded in real physics. The time dilation effects are not speculative, they're as solid as gravity. We've measured them countless times, and they always match Einstein's predictions precisely. Now let's discuss the engineering challenges of building a spacecraft that could reach even a fraction of light speed. These challenges are so enormous that they make our current space technology look like children's toys by comparison. The most efficient propulsion system we've seriously proposed is the antimatter rocket. When matter and antimatter collide, they annihilate completely, converting 100% of their mass into energy, unlike nuclear reactions which convert less than 1%. This gives antimatter rockets a theoretical efficiency that no other chemical or nuclear rocket could match. But there are staggering problems. First, antimatter doesn't exist naturally on Earth. We have to create it in particle accelerators, and the process is phenomenally inefficient. CERN, the European Organization for Nuclear Research, can produce about 1 billion antiprotons per minute. That sounds impressive until you realize that it would take 100 million years to produce just 1 gram of antimatter at that rate, and antimatter is expensive. Current estimates suggest it costs about $62 trillion per gram, making it by far the most expensive substance humans have ever created. You'd need tons of antimatter to fuel a journey to even the nearest star, an amount that would cost more than the entire global economy many times over. Second, storing antimatter is incredibly difficult. It annihilates instantly upon contact with normal matter, so you can't just put it in a tank. You need magnetic containment systems that suspend it in vacuum, never allowing it to touch the walls. Any failure, even for a microsecond, would result in an explosion that makes nuclear weapons look gentle. Third, even if you solve the production and storage problems, an antimatter rocket would produce incredible amounts of gamma radiation. The crew would need shielding so heavy that it would add enormous mass to the spacecraft, requiring even more fuel, which increases mass further in a vicious cycle. Despite these challenges, researchers haven't given up. Projects like NASA's Institute for Advanced Concepts have studied antimatter propulsion seriously. In 2004, physicist Robert Forward calculated that a spacecraft using an antimatter-catalyzed nuclear pulse propulsion system could theoretically reach 10% light speed. That would get you to Proxima Centauri in about 42 years, a time frame within a human lifetime. If you are enjoying this, make sure to subscribe to the channel. Here we explore the greatest mysteries humanity has ever faced, and you'll never miss a video that could completely change how you see reality. But even 10% light speed presents enormous challenges. At that velocity, you'd cover 300,000 kilometers every 10 seconds. Any collision with even a grain of sand would be catastrophic. The kinetic energy would be equivalent to tons of TNT detonating on impact. Your spacecraft would need incredible shielding or an advanced system to detect and vaporize debris before impact. Another propulsion concept is the fusion ramjet, first proposed by physicist Robert Bussard in 1960. The idea is elegant. Your spacecraft would use powerful magnetic fields to scoop up hydrogen atoms from interstellar space as it travels. These atoms would be funneled into a fusion reactor, providing fuel continuously so you'd never run out. The beauty of this design is that the faster you go, the more fuel you collect per second, potentially allowing continuous acceleration. Bussard calculated that such a ship could theoretically reach velocities very close to light speed given enough time. However, subsequent analysis revealed serious problems. The magnetic scoop would need to be enormous, hundreds of kilometers across, to collect enough diffuse interstellar hydrogen, and the drag created by the magnetic field interacting with charged particles in space might actually slow the spacecraft down more than the thrust from the fusion reactor could compensate for. The physics remain unclear, and we're still many decades away from controlled fusion power, even in stationary reactors on Earth. A more near-term possibility is the light sail, spacecraft propelled by radiation pressure from lasers or sunlight. Since photons carry momentum, when light reflects off a surface, it imparts a tiny push. A lightweight spacecraft with an enormous, ultra-thin reflective sail could be accelerated by a powerful laser array stationed in space or on the Moon. This concept has actually been tested on a small scale. The Planetary Society's LightSail 2, launched in 2019, successfully demonstrated controlled solar sailing in Earth orbit, using sunlight to change its orbit without any onboard propulsion system. For interstellar journeys, physicist Philip Lubin at the University of California, Santa Barbara, has proposed the Starshot project, backed by investor Yuri Milner and physicist Stephen Hawking before his death in 2018. The concept involves ultra-lightweight nano spacecraft, each weighing only a few grams, equipped with light sails about 4 meters across. A powerful array of Earth-based lasers would focus their beams on these tiny craft, accelerating them to 20% light speed within minutes. At that velocity, these tiny probes could reach Proxima Centauri in about 20 years and send back data using miniaturized electronics. The entire probe, including cameras, processors, and communication systems, would be smaller than a smartphone. It's an audacious vision, but the physics is sound. And the technology, while extremely challenging, doesn't violate any known laws of nature. Of course, there's a major limitation. Light sails can't slow down unless there's a laser at the destination or a star to reflect off. These probes would be flyby missions only, screaming past their target at 20% light speed with only minutes to gather data before disappearing into interstellar space forever. But even that would be revolutionary. We could have close-up images and measurements from another star system within our lifetimes. Let me bring this back to the human scale for a moment. All of these engineering challenges, all of these theoretical discussions, they're about one fundamental thing: our desire to explore, to reach out, to see what's beyond the next horizon. It's the same impulse that drove our ancestors to cross oceans in wooden boats, not knowing what they'd find or if they'd ever return. But the ocean has shores. Space has no shores, only distances so vast that light itself, the fastest thing in existence, takes years to cross them. When our ancestors looked up at the stars, they thought they were lights on a celestial sphere, just out of reach. Now we know each star is a sun, potentially with planets and life, but separated from us by gulfs of space that make the Earth's oceans look like puddles. The speed of light doesn't just limit our spacecraft, it limits our knowledge. When you look at Proxima Centauri through a telescope, you're not seeing it as it is now. You're seeing light that left that star 4.24 years ago. You're looking into the past. That star could have exploded yesterday, and you wouldn't know for another 4 years. The Andromeda Galaxy, that beautiful spiral you can see on dark nights with the naked eye, looks as it did 2.5 million years ago. You're seeing light that began its journey before humans existed, before Homo sapiens evolved. In that light, encoded in patterns of photons that have traveled through space for millions of years, is information about a galaxy that might look completely different now. The universe has a horizon, not because space ends, but because light hasn't had time to reach us from beyond a certain distance. The observable universe is about 93 billion light-years across, but the universe itself is likely much larger, possibly infinite. We're surrounded by regions of space whose light will never reach us, galaxies we can never see, civilizations, if they exist, that we can never contact. And because the universe is expanding, that horizon is actually shrinking in a sense. Galaxies that we can see today will, in the distant future, accelerate away from us faster than light due to cosmic expansion. Their light will be stretched to longer and longer wavelengths, becoming redder and dimmer until they fade from view entirely. In the unimaginably distant future, hundreds of billions of years from now, an observer in our galaxy would see only the local group of galaxies, with everything beyond swallowed by expanding space and darkness. This means that we, here now, live in a special time. We can see the cosmic microwave background radiation, the afterglow of the Big Bang. We can observe distant galaxies and study the universe's history. Future civilizations, if they exist trillions of years from now, won't have this privilege. They'll live in island universes, isolated, with no evidence that anything exists beyond their local group. In a sense, the speed of light creates loneliness on a cosmic scale. The universe is vast and possibly filled with life, but the distances are so enormous and the speed of light so limiting that we may be, for all practical purposes, alone. Even if there are 1 million intelligent civilizations in our galaxy, if they're thousands of light-years apart, meaningful communication would take millennia. You'd send a message, and your great-great-great-grandchildren might receive a reply. This creates what's called the Fermi paradox, named after physicist Enrico Fermi. If the universe is so vast and so old, and if life is reasonably common, where is everybody? Why haven't we detected any signals, any evidence, any artifacts of alien civilizations? One answer might be the speed of light itself. If interstellar travel is as difficult as physics suggests, then civilizations might be common but isolated, each confined to their own small region of space, unable to cross the enormous gulfs between stars. We might live in a universe full of life, with each species forever trapped on their own islands, able to wonder if anyone else is out there but never able to meet. Some scientists, like Carl Sagan, were optimistic that we might at least communicate via radio signals. Radio waves travel at light speed, and while a conversation would take years or centuries depending on distance, at least we could share knowledge and culture. Others, like physicist Stephen Hawking, warned that we should perhaps stay quiet, because any civilization capable of detecting our signals and crossing interstellar space would be so technologically advanced that the encounter might not go well for us. But there's something even stranger we need to discuss, something that challenges our intuitive understanding of cause and effect, the relationship between light speed and simultaneity. Einstein realized that if the speed of light is constant for all observers, then simultaneity, the concept of now, becomes relative. Here's what that means. Imagine two events happen. A supernova explodes in one galaxy, and at the same time, a planet forms in another galaxy a billion light years away. But same time, according to whom? There's no universal clock, no cosmic reference frame that defines absolute simultaneity. If you're moving at high speed relative to those galaxies, you might see the supernova happen first. Someone moving in the opposite direction might see the planet form first. You're both right. There's no absolute answer to which happened first. The order of events depends on your motion through space-time. This only applies to events that are far enough apart that light can't travel between them, what physicists call space-like separated events. For events where one could causally affect the other, where light has time to travel from one to the other, all observers agree on their order. Cause always precedes effect. The universe preserves causality, but it does so at the cost of absolute simultaneity. Think about what this means for consciousness and existence. When you think right now, you're imagining a slice of time that encompasses the whole universe at this instant. But that slice doesn't exist in any objective sense. Right now, on a planet orbiting Proxima Centauri is undefined. Depending on your motion, now there could be 4 years in the past or 4 years in the future relative to any given observer. This has profound philosophical implications. The universe doesn't have a universal present moment. Past, present, and future are relative concepts dependent on the observer. In a very real sense, all moments in time exist simultaneously in the four-dimensional structure of space-time, what physicists call the block universe. In this view, the past hasn't ceased to exist, and the future isn't yet to be. Everything that has happened and will happen exists as different regions of space-time. Your birth, you're reading this right now, your death, all exist as events at different coordinates in space-time. Time is just another dimension, like space, and your consciousness is moving along your world line. Your path through space-time, experiencing one moment after another, this is called eternalism or the block universe theory, and it's a natural interpretation of relativity, though not the only one. It suggests that free will might be an illusion, that the future is already determined, already exists out there in space-time, and we're simply experiencing it moment by moment. Other interpretations, like the growing block universe or presentism, try to preserve a meaningful distinction between past, present, and future, but they struggle to reconcile with relativity's implications. Now let's explore another consequence of light speed limitation: information and entropy. The second law of thermodynamics states that entropy, roughly speaking disorder or randomness, always increases in closed systems. Information is closely related to entropy. When you erase information, you increase entropy. When you create information, you must decrease entropy somewhere else, typically by expending energy. But information can't travel faster than light. This creates fundamental limits on computation and information processing. If you have a computer processor where different parts need to communicate, the maximum speed at which information can travel between those parts is the speed of light. This limits how fast any computer can operate. Modern computer chips are already approaching these limits. A signal traveling at light speed can cross only about 30 centimeters in 1 nanosecond, 1 billionth of a second. Computer processors operating at gigahertz frequencies, billions of cycles per second, have to deal with the fact that light can only travel a few dozen centimeters during each clock cycle. This is why computer engineers work so hard to make chips smaller. Shorter distances mean faster communication. There's a theoretical limit called the Bekenstein bound, proposed by physicist Jacob Bekenstein in the 1970s. It states that there's a maximum amount of information that can be stored in a given region of space with a given amount of energy. The limit depends on the energy and the size of the region, but it's ultimately derived from fundamental physics, including the speed of light and quantum mechanics. For a sphere of matter with a given radius and mass, the maximum information content is proportional to the surface area of that sphere, not its volume. This has profound implications for black holes and leads to the holographic principle, the idea that all the information in a three-dimensional region of space might be encoded on its two-dimensional boundary. This principle suggests that the universe might be fundamentally two-dimensional, with the third dimension being an emergent property, like a hologram that appears three-dimensional but is actually projected from a two-dimensional surface. Some physicists think this could be key to reconciling quantum mechanics and gravity, two theories that have resisted unification for almost a century. But I'm getting ahead of myself. Let's return to the speed of light and its role in causality. The cosmic speed limit ensures that causes precede effects. Without this limit, without the light speed barrier, the universe would be chaotic. Events could affect their own past, creating paradoxes and inconsistencies. Imagine you could send a signal faster than light. Due to relativity of simultaneity, some observers would see that signal traveling backward in time from their perspective. You could send information to your own past, creating a causal loop. You could prevent the very event that caused you to send the signal, creating a contradiction. These are called closed time-like curves in the mathematics of general relativity, loops in space-time where you could return to your own past. Some solutions to Einstein's field equations, like the Gödel metric or certain configurations involving rotating black holes or wormholes, seem to allow closed time-like curves. But most physicists believe these solutions don't correspond to physical reality, or that some principle we don't yet understand prevents them from occurring. Stephen Hawking proposed what he called the chronology protection conjecture. The laws of physics prevent time machines and closed time-like curves, protecting the universe from paradoxes. We don't have a proof of this conjecture, but every time we've found a potential way to create a time machine in theory, we've discovered that it requires exotic conditions that probably can't exist, like negative energy or infinite density. The speed of light stands as the guardian of causality, the boundary that keeps the universe logically consistent. It's not just a speed limit on motion, it's a fundamental constraint on reality itself. Let's now consider black holes, objects so dense that their escape velocity exceeds light speed. At the event horizon, the boundary of a black hole, the escape velocity equals exactly light speed. Anything closer than that, even light itself, cannot escape. Information that crosses the event horizon is lost to the outside universe forever, or so we thought. Stephen Hawking showed in the 1970s that black holes aren't completely black. Due to quantum effects near the event horizon, they emit radiation, now called Hawking radiation. This radiation carries energy away from the black hole, causing it to slowly evaporate over enormous timescales. A black hole with the mass of our Sun would take 10 to the power of 67 years to evaporate, far longer than the current age of the universe. But Hawking's discovery created a paradox. The radiation is thermal, meaning it's random and carries no information about what fell into the black hole. If a black hole forms, swallows information, and then evaporates completely, where did that information go? Quantum mechanics says information can't be destroyed, but general relativity says it disappears behind the event horizon. This is the black hole information paradox, one of the deepest unsolved problems in theoretical physics. It's a conflict between quantum mechanics and general relativity, the two most successful theories we have, and resolving it requires understanding quantum gravity, a theory we don't yet possess. Recent developments suggest that information might be preserved through subtle quantum correlations in the Hawking radiation, encoded in ways we're only beginning to understand. This involves concepts like quantum entanglement, where particles become connected such that measuring one instantly affects the other, regardless of distance. This brings us to one of the most mysterious aspects of quantum mechanics, quantum entanglement and its relationship to the speed of light. When two particles are entangled, measuring a property of one particle instantly determines the corresponding property of the other, even if they're separated by light years. Einstein called this spooky action at a distance and believed it showed that quantum mechanics was incomplete. But here's the crucial point. Entanglement doesn't allow faster-than-light communication. When you measure an entangled particle, you get a random result. The other particle's measurement will be correlated, but there's no way to control what result you get, so you can't use this to send information. You'd need to compare your results with the other observer's results, using conventional light-speed limited communication to even detect the correlation. This has been tested extensively. In 2017, Chinese scientists used the Milliseconds satellite to create entangled photons and send them to ground stations over 1,200 kilometers apart. The correlations were exactly as quantum mechanics predicted, but no information traveled faster than light. The universe preserves its speed limit through the inherent randomness of quantum measurements. Some interpretations of quantum mechanics, like the many worlds interpretation, suggest that entanglement doesn't involve any faster-than-light influence at all. Instead, the universe branches into multiple versions, and the correlations arise because you and the distant observer are in matched branches of a splitting reality. Other interpretations, like pilot wave theory, do involve faster-than-light influences, but in ways that can't be used for communication or to violate causality. The debate continues, but what's clear is that the speed of light as a limit on information transmission remains intact. Whatever quantum mechanics is telling us about reality, it respects Einstein's cosmic speed limit. Now, let me address something that often confuses people: the expansion of space itself. The universe is expanding and distant galaxies are moving away from us. Some of them are receding faster than light. How is this possible if nothing can move faster than light? The answer is that the speed of light limit applies to motion through space, not to the expansion of space itself. Space can stretch, and it can stretch faster than light. Imagine dots on a balloon surface as it inflates. The dots themselves aren't moving across the balloon. The rubber between them is stretching. Similarly, galaxies aren't moving through space faster than light. Space itself is expanding between them. This means there are galaxies we can see whose light is reaching us, but which are now, accounting for continued expansion, receding from us faster than light. We can observe them because their light was emitted when they were closer and was already en route, before space expanded enough to carry them beyond the cosmic event horizon. There's also a subtle point about what we mean by now for distant galaxies, given what we discussed about simultaneity. In cosmology, physicists use a specific reference frame called the comoving frame, which defines a cosmic time that applies to the universe as a whole. In this frame, the universe has an age, about 13.8 billion years, and we can meaningfully talk about distant galaxies existing now, even though we can't see them as they are now. But this is a convention, a useful way of thinking about cosmology, not an absolute truth. Different observers in different states of motion would define simultaneity differently, though for practical purposes, almost everything in the observable universe is moving slowly compared to light speed, so the differences are small. The expansion of space also affects light itself. As light travels through expanding space, its wavelength stretches, becoming redder. This is cosmological redshift, and it's how we measure distances to faraway galaxies. The more redshifted the light, the farther away the galaxy, and the faster space is expanding between us. Eventually, about 47 billion light-years away, that's the current distance accounting for expansion. Space is expanding faster than light. This boundary is called the cosmic event horizon. Light emitted from beyond this horizon will never reach us, no matter how long we wait, because space is stretching faster than light can cross it. This means there are parts of the universe that are forever beyond our reach, not just practically but fundamentally. Even if we could travel at light speed, we couldn't reach them because space itself is expanding too fast. The observable universe is a sphere surrounding us, and beyond that sphere is the unobservable universe, potentially infinite in extent, full of galaxies and stars and possibly life that we will never see, never contact, never know about. Think about that for a moment. The universe might be infinite, but we're confined to observing only a finite bubble around us. And as the universe ages and expansion continues, that bubble, in a sense, is shrinking. Galaxies near the edge are disappearing over the cosmic horizon, and future observers will have less of the universe to study than we do. In 1 trillion years, the night sky will look very different. The Milky Way will have merged with Andromeda and a few other local galaxies, forming a single large galaxy. But beyond that galaxy, the sky will be mostly empty. The cosmic microwave background radiation will have cooled and stretched to undetectable wavelengths. An astronomer in that distant future would look at the universe and conclude it's just one galaxy surrounded by empty space, with no evidence of the Big Bang, no evidence of cosmic expansion, no evidence of the rich universe we see today. This has led some physicists to wonder, might we be in a similar situation now? Could there be evidence of earlier cosmic events that has already disappeared beyond our horizon? Could the universe be far older and far larger than we can detect? We might be as limited in our view as those future astronomers, unaware of what lies beyond our observational reach. The speed of light, combined with cosmic expansion, creates a fundamental limitation on knowledge itself. There are questions about the universe that might have no answer, not because the answer is complex or difficult, but because the relevant information simply cannot reach us. Let's pivot to something more immediate: how the speed of light affects our daily lives. GPS satellites orbiting Earth rely on precise timing to calculate positions. They broadcast signals that include timestamps, and your GPS receiver calculates how long the signal took to arrive, multiplying that time by the speed of light to determine distance. By comparing signals from multiple satellites, it triangulates your position. But there's a problem. The satellites are moving at high speed and are higher in Earth's gravitational field than you are. Both of these factors cause time dilation. Special relativity due to the satellite's motion makes their clocks run slower by about 7 microseconds per day. General relativity, due to weaker gravity at their altitude, makes their clocks run faster by about 45 microseconds per day. The net effect is that satellite clocks run about 38 microseconds faster per day than clocks on Earth's surface. 38 microseconds doesn't sound like much, but light travels about 11 kilometers in that time. If GPS satellites didn't account for relativity, positions would be off by kilometers after just one day, and the system would be useless within minutes. Every time you use GPS to navigate, you're depending on Einstein's theories of relativity. The speed of light and time dilation aren't abstract concepts, they're engineering requirements for modern technology. The same principles apply to particle accelerators, like the Large Hadron Collider at CERN. Protons are accelerated to 99.999991% the speed of light, so close that they circle the 27-kilometer ring about 11,000 times per second. At this speed, relativistic effects are enormous. From our perspective, the protons take about 90 microseconds to complete one lap. But from the proton's perspective, time is dilated by a factor of about 7,000. The proton experiences only about 13 nanoseconds per lap, and due to length contraction, from the proton's perspective, the entire 27-kilometer ring is contracted to less than 4 meters. The proton doesn't think it's moving near light speed. From its reference frame, it's the ring that's moving, and the ring is squashed to a tiny circle. Both perspectives are equally valid. There's no absolute answer to how long the ring really is or how much time really passes. The answer depends on your reference frame, and all inertial reference frames are equally valid. This is the principle of relativity that Einstein built his theories on. The laws of physics are the same in all inertial reference frames, and the speed of light is constant for all observers, regardless of their motion. Without understanding relativity and the speed of light, none of this would be possible. Modern physics, modern technology, our understanding of the cosmos, all rest on Einstein's insight that light speed is constant and represents a fundamental limit. But let's return to a question that might be nagging at you. Why is the speed of light exactly 299,792,458 meters per second? Why that specific number? The answer is both profound and anticlimactic. It's arbitrary. The meter was originally defined as 1/10,000,000th of the distance from the North Pole to the equator through Paris. The second was defined as 1/86,400th of a mean solar day. These are human constructs, convenient divisions of physical quantities, but ultimately arbitrary. The speed of light in those units just happens to be about 300 million meters per second. If we'd chosen different units, the number would be different. The fundamental thing isn't the number. It's that there exists a maximum speed, a cosmic speed limit, and that this speed relates space and time to each other. In fact, many physicists prefer to use units where the speed of light is simply 1. In these natural units, velocity is expressed as a fraction of light speed. A spacecraft traveling at half light speed has a velocity of 0.5, not 150 million meters per second. Time and distance become interchangeable. A light year is both a distance and a time, 1 year. In this system, Einstein's equation energy and mass are the same thing, measured in the same units. This reveals something deep. Mass is simply a form of energy, concentrated energy with the property of inertia. When you hold an object, most of its mass doesn't come from the quarks and electrons that make up its atoms. It comes from the binding energy holding those quarks together, the energy of the strong nuclear force that confines quarks inside protons and neutrons. So the speed of light isn't just a speed limit, it's the conversion factor between space and time, between energy and mass. It's woven into the fabric of reality at the deepest level. Asking why it has the value it does in arbitrary human units is like asking why a circle has 360 degrees. The number is a human choice. The underlying geometry is fundamental. But there is a deeper question. Could the speed of light have been different? Could there be universes with different values of fundamental constants, including the speed of light? This ventures into speculative territory, but it's a serious question in theoretical physics. If the speed of light were much slower, say 100 meters per second, the universe would be radically different. Chemical reactions depend on electromagnetic forces which propagate at light speed. Atoms themselves might be unstable. Stars might not be able to form or might burn out instantly. Complex chemistry and biology would likely be impossible if the speed of light were much faster. Approaching infinity, we'd have something closer to Newtonian physics, where information travels instantaneously and simultaneity is absolute. But quantum mechanics depends on relativity. Particles behave as they do, partly because of relativistic effects at small scales. A different light speed would mean different physics at every level. Some physicists speculate that we live in a multiverse, a vast ensemble of universes with different values of fundamental constants. In this view, we happen to live in a universe where the constants allow complexity, chemistry, stars, planets, and life. This is the anthropic principle. We observe the values we do because only in a universe with these values could observers exist. It's a controversial idea. Some see it as a profound insight into why the universe seems fine-tuned for life. Others see it as untestable speculation beyond the reach of science. The debate continues, but what's clear is that the speed of light is precisely what it needs to be for our universe to exist as it does. Let me share something that captures the strangeness of light speed and relativity, the twin paradox. Imagine identical twins, Alice and Bob. Alice stays on Earth while Bob travels in a spacecraft to a distant star at near light speed, then returns. When they reunite, Bob has aged less than Alice. Time passed more slowly for Bob because he was moving at relativistic speeds. This isn't just theory. It's been confirmed countless times with atomic clocks on aircraft and satellites. In 1971, physicists Joseph Hafele and Richard Keating flew atomic clocks around the world on commercial airliners. When they compared the traveled clocks to reference clocks that stayed on the ground, the traveled clocks showed less elapsed time, exactly as relativity predicted, accounting for both their motion and changes in gravitational time dilation. But here's what makes it a paradox. From Bob's perspective, it's Alice who's moving. He's at rest in his spacecraft, and Earth is moving away then returning. So shouldn't Alice age less than Bob? How can they both age less than each other? The resolution is that the situation isn't symmetric. Bob accelerates when his spacecraft turns around to come home. Acceleration breaks the symmetry. Bob transitions between reference frames, experiencing forces that Alice doesn't experience. Alice remains in a single inertial reference frame the whole time. Only Bob's reference frame changes, and that makes all the difference. During Bob's turnaround, when he decelerates, stops, and accelerates back toward Earth, from his perspective, Alice's clock suddenly jumps forward. The act of changing reference frames shifts what Bob considers now on distant Earth. This jump more than compensates for the slower rate at which he saw Alice's clock running during his outbound and return journeys. This is profoundly weird. The act of accelerating doesn't just change your velocity, it changes your definition of simultaneity, your slice through space-time that represents now at distant locations. Events that haven't happened yet from one perspective have already happened from another perspective after you accelerate. The present moment is observer-dependent, malleable, shifting with motion. This connects to something called the Ritdik-Putnam-Penrose argument. which suggests that if simultaneity is relative, then the future must already exist in some sense. If what counts as now on a distant planet depends on my motion, and I can change my motion at will, then all moments must exist simultaneously in space-time. The future isn't yet to come. It's already out there, and my consciousness is simply moving along my world line, experiencing it moment by moment. Not all physicists accept this interpretation. Some argue that there's a meaningful distinction between existence and accessibility, that the future exists potentially but not actually until it enters our past light cone, the region of space-time that could have causally affected us. But the mainstream view in physics is the block universe, where all of space-time exists as a four-dimensional whole, and past, present, and future are equally real. If this is true, what does it mean for free will? If the future already exists, are our choices predetermined? This is an ancient philosophical question, but relativity gives it new urgency. If someone in a distant galaxy moving at high speed relative to us can consider our future to be now from their perspective, then that future must already be determined, already exist. Some philosophers argue that this shows free will is incompatible with relativity. Others argue that free will is still compatible, because what matters is not whether the future exists, but whether your choices are causally effective, whether you play a role in determining what that future contains. Your future self reading these words might exist in the block universe, but that doesn't mean your present self didn't freely choose to continue reading. This is deep water, and I don't have definitive answers. What I can tell you is that relativity has transformed not just physics but philosophy, forcing us to reconsider basic concepts like time, causality, and existence itself. Now let's consider one more consequence of light speed limitation, the Fermi paradox. The universe is vast, containing perhaps 2 trillion galaxies, each with hundreds of billions of stars. Many of those stars have planets, and recent discoveries suggest planets are the rule rather than the exception. If even a tiny fraction harbor life, and a tiny fraction of those develop intelligence and technology, there should be millions or billions of technological civilizations in the observable universe. So where is everyone? Why haven't we detected any signs of alien civilizations? This is the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where are they?" The speed of light offers a partial answer. Even if advanced civilizations exist, the distances between stars are so vast that contact would be extraordinarily difficult. The nearest star to our Sun is Proxima Centauri, 4.2 light-years away. A radio signal traveling at light speed would take over 4 years to reach there, and another 4 years for a reply. A conversation with the nearest possible aliens would involve 8-year delays between messages. The time and energy required for interstellar travel are enormous, even traveling at 1/10 light speed, which would require fantastically advanced propulsion technology. A journey to Proxima Centauri would take 42 years. The travelers would age 42 years, though due to time dilation, slightly less than that, about 41 years at 1/10 light speed. For destinations hundreds or thousands of light-years away, the journey times become impractical for biological beings. Perhaps advanced civilizations send robotic probes instead, self-replicating machines that explore the galaxy over millions of years. But even at high fractions of light speed, colonizing or exploring the entire Milky Way would take millions of years. If civilizations are common, someone should have done this by now. The galaxy is over 10 billion years old, far older than human civilization. There's been plenty of time for expansion, yet we see no evidence of it. Some solutions to the Fermi paradox suggest we're alone, that life or intelligence is far rarer than we think. Others suggest civilizations destroy themselves before achieving interstellar travel. Still others propose that advanced civilizations exist, but are deliberately hiding, or that they exist in forms we don't recognize, or that they're here but we haven't noticed. Another possibility is that the speed of light limitation is simply too severe. Perhaps interstellar travel is so difficult that civilizations remain confined to their home star systems. Perhaps they communicate via methods we haven't discovered yet, or perhaps they tried radio and have moved on to something else. We've only been listening for about 60 years, a blink in cosmic time. The universe might be teeming with life, all of it isolated by the tyranny of distance and the speed limit of light. Each civilization arises, flourishes, and dies in isolation, separated from its neighbors by gulfs too vast to cross. The light from their radio transmissions might be traveling through space right now, carrying messages we'll detect centuries or millennia from now, long after the civilizations that sent them have vanished, or perhaps we're the first. In the vast sweep of cosmic history, someone has to be first. Maybe it's us. Maybe we're the civilization that will one day colonize the galaxy, seeding it with life and intelligence, becoming the ancestors that future civilizations will wonder about. The silence might not be a mystery to be solved, but an opportunity to be seized. But I'm speculating now. The truth is, we don't know. The speed of light limits not just our ability to travel, but our ability to know, creating islands of isolation in the cosmic sea. Let me share one final thought about light speed and its role in the universe. The speed of light connects to fundamental constants in surprising ways. There's a dimensionless number called the fine structure constant, approximately 1 divided by 137, that describes the strength of electromagnetic interactions. This constant appears everywhere in physics, from the spectrum of hydrogen to the behavior of particles in quantum field theory. The fine structure constant is related to the speed of light, the charge of an electron, and Planck's constant. These quantities aren't independent, they're connected by deep relationships. If you change the speed of light, you change the fine structure constant, which changes chemistry, changes how atoms behave, changes everything. Some physicists have speculated that the fine structure constant might vary across space or time. If so, the speed of light might also vary. There have been controversial claims of detecting such variations by analyzing light from distant quasars, but most physicists remain skeptical. The evidence is weak, and systematic errors are hard to rule out. If the constants do vary, it would revolutionize physics. We assume the laws of physics are the same everywhere and at all times, but if fundamental constants change, that assumption breaks down. The universe might be far stranger than we imagine, with different regions having different physics, or the laws evolving over cosmic time. But as of now, all evidence suggests the speed of light is constant, unchanging, the same everywhere in the observable universe at all times. It's one of the most precisely measured quantities in physics, and within measurement precision, it never varies. This constancy is reassuring. It means the universe is comprehensible, that the laws we discover here apply everywhere. A star 10 billion light-years away obeys the same physics as our Sun. An atom in a distant galaxy behaves like an atom on Earth. The speed of light is the thread that connects it all, ensuring consistency across space and time. Every photon that enters your eye has a story. The light from your computer screen was emitted nanoseconds ago. The light from the Sun left its surface 8 minutes and 20 seconds ago. The light from the nearest star, Proxima Centauri, began its journey over 4 years ago. The light from the Andromeda galaxy left when humans were crafting the first stone tools 2.5 million years ago. The cosmic microwave background radiation has been traveling for 13.8 billion years, carrying information about the infant universe. You are not seeing the universe as it is. You are seeing the universe as it was, a patchwork of different moments stitched together by the travel time of light. Your perception of now is an illusion created by your brain, which interprets the light arriving at your eyes as simultaneous, even though it left its sources at vastly different times. This is true not just for vision, but for all information. Everything you know about the universe is based on signals that traveled to you at or below the speed of light. You are always living in the past, observing a universe that no longer exists in the form you perceive it. The present is inaccessible, hidden behind the speed of light delay, and yet this limitation has given us profound insights. By studying the speed of light, we discovered that time is relative, that space and time are unified, that mass and energy are equivalent. We learned that the universe has a structure, a geometry, that gravity is the curvature of space-time, that black holes exist where that curvature becomes extreme. We discovered that the universe is expanding, that it had a beginning, that it will likely expand forever, growing colder and darker until the last stars burn out, and black holes evaporate in a process that will take googles of years. We learned that quantum mechanics and relativity are both true, even though they seem incompatible, and that their reconciliation might require new physics we haven't yet discovered. All of this from studying light, from measuring its speed, from taking seriously the implications of its constancy. The speed of light is more than a scientific fact. It's a window into the deep structure of reality. It tells us that the universe has rules, laws that apply everywhere and always. It tells us that space and time are not separate but interwoven, that causality has a speed limit, that information cannot travel instantaneously. It tells us that we are isolated in space and time, that the vast majority of the universe is beyond our reach, perhaps forever. But it also tells us that the universe is knowable, that the same physics that applies here applies there, that by studying the light that reaches us, we can understand events that happened billions of years ago and billions of light years away. When you look at the night sky, you are doing cosmology. You are observing the universe's history, seeing light that has traveled across space and time to reach you. You are connected through that light to distant stars and galaxies, to events long past, to the deep past of the cosmos itself. The speed of light sets the tempo of the universe. It determines how fast signals can propagate, how quickly information can spread, how fast causality operates. It's the drummer keeping time while the cosmic dance unfolds, ensuring that cause precedes effect, that the laws of physics remain consistent, that the universe makes sense. Einstein called it the speed of light, but it's more accurate to call it the speed of causality, or simply the speed of information. Light travels at this speed, but so do gravitational waves, gluons, and any massless particle. It's the speed at which the universe updates, the speed at which reality propagates. And here's something beautiful, you can measure it yourself. With simple equipment, a microwave oven and a chocolate bar, you can estimate the speed of light. Put the chocolate in the microwave with the turntable removed, run it for a few seconds, and look for hot spots where the chocolate melts. These hot spots are where the microwave standing waves have antinodes. Measure the distance between spots, double it to get the wavelength, multiply by the microwave frequency, usually 2.45 gigahertz, and you get the speed of light. It won't be precise, but you'll get a number around 300 million meters per second. You'll have measured one of the fundamental constants of the universe in your kitchen. Or consider this. The next time you use GPS, remember that the satellites overhead are running clocks corrected for relativistic time dilation. The speed of light isn't just an abstract concept. It's engineered into the technology you use every day. When you see lightning and hear thunder seconds later, you're experiencing the difference between light speed and sound speed. Light reaches you almost instantly. Sound takes about 3 seconds per kilometer. Count the seconds between flash and thunder, divide by 3, and you know how far away the lightning struck. These everyday experiences are reminders that the speed of light is real, measurable, consequential. It's not just something physicists worry about. It shapes your experience of the world, even if you don't consciously think about it. As I bring this to a close, I want to emphasize one final point. The speed of light represents a profound truth about the universe. Reality has a speed limit. Information cannot travel infinitely fast. Causality requires time to propagate. These aren't arbitrary restrictions. They're fundamental features of space-time itself. This means the universe has a structure, a logic, a consistency. It means that the laws of physics are the same everywhere, that the universe is comprehensible, that science is possible. Without the speed of light as a universal constant, there would be no relativity, no causal structure, perhaps no coherent physics at all. The speed of light is the thread that holds the cosmic tapestry together. It connects quantum mechanics to relativity, energy to mass, space to time. It's woven into every equation, every prediction, every measurement in modern physics. And it all started with a simple question: how fast does light travel? From that question came Maxwell's equations, special relativity, general relativity, quantum field theory, the Standard Model, cosmology, our understanding of black holes and the Big Bang, one constant, 300 million meters per second, and the entire edifice of modern physics. So when you see light, whether from a candle flame or a distant star, remember, you're witnessing something fundamental. Those photons have traveled at the cosmic speed limit, the fastest anything can travel, connecting you to their source through the fabric of space-time itself. The universe speaks to us in light, and light travels at exactly the speed it must for the universe to make sense, for causality to function, for time and space to weave together into the four-dimensional reality we inhabit. That's the speed of light, not just a number, but a window into the deepest truths about existence itself. Think light speed is fast. Click this next video on the screen and discover why even traveling at 300 million meters per second wouldn't be nearly enough to explore our cosmic neighbor. This will change how you see cosmic distances forever.